Well, we'll be discussing certain formula which are important from the point of view of competitions, and these formulae are regarding the concentration of solutions. What do you actually mean by concentration? For example, you take a beaker. In this beaker, let's say you take 100 grams of water, right? And to this you add 50 grams of salt. Now the amount of salt, that is 50 grams, upon the total amount of solution, that is 100 plus 50 multiplied by 100, gives you the percentage, gives you the concentration. Okay, so the concentration basically is the amount of solute dissolved in a given amount of solvent to make up a solution. So if I try taking out the concentration over here, this will be 50 upon 150 into 100, that is 53 is a 150, so it will be 33.33%. Concentration terms that we'll be using will be A, mass by mass percentage, B, mass by volume percentage, C, volume by volume percentage, D, molarity, E, molality, F, normality, the very first that we'll be discussing will be A, mass by mass percentage. Now what this implies is mass of solute divided by mass of solution multiplied by 100. Supposing you have 20 grams of sugar dissolved in 180 grams of water, then mass by mass percentage is 20 upon 20 plus 180 into 100. This is equal to 20 upon 200 into 100, and this gives you 10%. So mass by mass percentage is 10%. And one thing to be remembered is it is independent of temperature, because mass does not depend on temperature. In fact, these questions are generally asked which of the concentration terms depends on temperature. So mass by mass percentage does not depend on temperature. Mass by volume percent. Just a second. Mass by volume percent. The formula is mass of solute divided by volume of solution into 100. Supposing we have 20 ml of glycerol or glycerine and we add water to make up the solution to 400 ml. So this becomes 20 upon 400 into 100. So this is 4. So this becomes 5%. Now remember one thing, both mass by volume percent and volume by volume percent depend on temperature. Reason being, volume depends on temperature. So if temperature increases, volume will increase, and if temperature goes down, volume will go down. Then a third term is volume by volume percentage. So formula for this is volume of solute upon volume of solution into 100. So let's say you have 40 ml of alcohol dissolved in 160 ml of water. So its volume by volume percentage will be 40 upon 40 plus 160 into 100. So this comes as 40 upon 200 into 100, and this becomes 100 to the 20%. Now discuss molarity. Is designated by capital M and its formula is number of moles of solute divided by volume of solution into 1000, because volume is to be in liters. So now let's take an example. 2.46 grams of sodium hydroxide is dissolved in water and the solution is made up to 100 cc. Calculate molarity. So now what we have is number of moles of solute or number of moles of sodium hydroxide. This is equal to mass of sodium hydroxide divided by its molar mass. Let's first determine what the molar mass is of sodium hydroxide. This is equal to given mass of sodium hydroxide upon its molar mass. Molar mass, this is equal to NaOH you have, so Na is 23 plus 16 plus 1, this is equal to 40U. So number of moles is equal to given mass, which is 2.46, divided by molar mass, that is 40, and this comes out to be 0.0615. Now our next step is to derive molarity. So this will be number of moles of sodium hydroxide, which is 0.0615, divided by 100 multiplied by 1000. So this will be 0.615 m. One thing to be remembered is molarity has the volume term. Okay, so, and volume, you know, depends on temperature. So if temperature increases, volume will increase, and if temperature decreases, volume will decrease. And here volume term is in the denominator. So if volume increases, molarity will go down, and if volume decreases, molarity will increase. Now molarity actually means, first of all, the symbol of molarity is small m, and this is equal to, small m is equal to number of moles of solute per kilogram of solvent. So when we write the formula, this becomes small m is equal to moles of solute upon mass of solvent multiplied by 1000, because it has to be in kilograms, right? So this is the formula. Now one thing you have to remember, that you can see for yourself that in the denominator or the numerator you do not have the volume term. So this is not dependent on temperature. It's an oft asked question, that whether it is dependent on temperature or not. So this is not dependent on temperature. Molarity is dependent, but this is not dependent on temperature. Let's take an example. You have a question here. A sugar syrup of weight 214.2 grams contains 34.2 grams of sugar. Calculate molality. Now what you have to remember here is, this is your question in fact. So what you have to remember is, the formula of sugar is the formula of cane sugar, that is C12H22O11. First let's take out the molar mass of this, because it will come handy to us. 12 multiplied by 12 plus 1 multiplied by 22 plus 16 multiplied by 11. So this comes as 44 sorry, this is 144 plus 22 plus 11 6 is 66, 176. So this is as 342 U. Always remember the molar mass of sugar as cane sugar as 342 U because it's generally asked. So now you have the solution to this question, and that is, now beta, this is sugar syrup. Sugar syrup means sugar plus water, right? And they have said the weight of sugar syrup is 214.2, and this is equal to weight of sugar, that is 34.2, plus the weight of water, right? So weight of water will be, that will be equal to 214.2 minus 34.2, and that will be equal to 180 grams. So 180 grams is the mass of the solvent. So molality is moles of solute upon mass of solvent multiplied by 1000, as I previously mentioned. So moles of solute, that is N, is equal to given mass of sugar, that is 34.2, right, upon molar mass of sugar, that is 342, and this comes out to be as 0.1. So you have 0.1 moles of sugar, right? Mass of solvent is equal to 180 grams or 0.18 kilograms, right? So our molality becomes 0.1 upon 0.18. So this is equal to 0.56. So 0.56 as a molality. Normality, it implies gram equivalence of solute dissolved in 1 liter of solution. I'll just tell you what gram equivalence is, or we can write normality as gram equivalence of solute upon volume of solution in liters. Now here again you see that the volume term is there and it is there in the denominator. So if temperature increases, volume will increase, and if volume increases, normality will decrease. So volume, temperature and normality, they are inversely proportional to each other. This is again a question which is generally asked in a competition, so please mind it. If temperature increases, volume, normality will decrease, and if normality decreases, if temperature decreases, normality will increase. Now what is gram equivalence? This is equal to mass of solute upon its equivalent weight. Now we come across what is actually equivalent weight. And equivalent weight is, this is molecular mass divided by acidity in case of bases slash basicity in case of acids slash valency. If it's neither an acid or a base, it's a salt. Now let's take out the, let's say, equivalent weight of sulfuric acid. Sulfuric acid. This is equal to molecular mass of sulfuric acid 1 multiplied by 2 plus 32 plus 16 multiplied by 4. Now sulfuric acid gives 2 H plus ions in solution. So we will divide this by 2. So this will be equal to 98 upon 2 is equal to 49. So 49 is the equivalent weight of sulfuric acid. Let's take one more example. Let's determine the equivalent weight of sodium hydroxide. Now the molar mass of sodium hydroxide is 23 plus 16 plus 1. Now sodium hydroxide gives 1 OH minus ion in solution. So its basis acidity is 1. So we will divide this molecular mass by 1. So this will be equal to 40 upon 1. So 40 is the equivalent weight of sodium hydroxide. Let's take one more example. This is neither an acid nor a base, it's sodium sulfate, which is a salt. Its molar mass is 23 multiplied by 2 plus 32 plus 16 multiplied by 4 divided by, now this gives 2 Na plus ions in solution and a bivalent sulfate ion in solution. So its valency will be 2. So we will divide it by 2 and it comes out to be 142 upon 2. This is equal to 71. So 71 is the equivalent weight of sodium sulfate. Well, now let's take up a numerical, and the question is, calculate the normality of (31.5 grams) of hydrated oxalic acid formula is in 1250 ml of solution, right? First we'll find the equivalent weight of oxalic acid, that is hydrated oxalic acid. This is equal to 1 multiplied by this, the formula is whole twice dot 2H2O. So this will be equal to 12 plus 16 plus 16 plus 1 into 2 plus 2 into 1 multiplied by 2 plus 16. So this comes out to be 126, and because its basicity is 2, oxalic acid, or you can write it like this, it gives 2 H plus ions in solution. So its basicity is 2. So we will write this as 126 divided by 2, that is 63. 63 is the equivalent weight of oxalic acid, right? So gram equivalence is equal to mass upon equivalent weight. This is equal to 31.5 upon 63 and this is equal to 0.5. So when we have to take out the normality, normality is gram equivalence upon volume of solution multiplied by 1000. So this will be gram equivalence is 0.5, volume of solution is 1250 ml multiplied by 1000. So this comes out to be 0.4 N. Now what is actually empirical formula? Let's consider this molecule C6H6. Now C6H6 is its molecular formula. Right? It gives the exact number of atoms of elements in the molecule. Same ways, you have C6H12O6, 6 atoms of carbon, 12 atoms of hydrogen and 6 atoms of oxygen. So this is the molecular formula. It gives the exact number of atoms of each of the elements carbon, hydrogen and oxygen in the molecule glucose. Now if we look at the ratio of these atoms of different elements, we see the ratio 6:12:6, that is 1:2:1. So we can write this as CH2O. Now CH2O is nothing but the empirical formula. Same ways, in the benzene molecule C6H6, this is the molecular formula. It gives the exact number of atoms of carbon and hydrogen in the molecule benzene. But if we look at the ratio 6:6, this is nothing but 1:1, the simplest ratio. And we can write the formula as CH. This is the empirical formula. So the empirical formula gives you the ratio of atoms of different elements present in a molecule. Now how do we calculate it? How do we determine the empirical formula? Let's get to this. Supposing the question is percentage of carbon is equal to 92.3 and hydrogen is equal to 7.7 in a molecule. Molecular mass is given as 78U. Determine empirical and molecular formula. Okay, so what do we do is, first of all, we'll make columns. In this we'll write the names of the elements. Then here we will write the percentage. This is 92.3% and this is 7.7%. In the second column we'll write the atomic mass. The atomic mass of this is 12 and this is 1. In the third column we will divide 92.3 by 12, and when we divide 92.3 by 12 we get something like 7.6%, sorry, and when we divide 7.7 by 1 we get 7.7. Now the one which is the least of the two, we'll divide the rest of it by it. So we'll divide 7.6 by 7.6 and we'll get 1, and we'll divide 7.7 by 7.6 and we'll get approximately 1. So the empirical formula is CH, that is one atom of carbon and one atom of hydrogen. This is how we determine the empirical formula. Now how do we determine the molecular formula? For molecular formula, we have to take out the value of N. N is equal to molecular mass upon empirical formula mass. So molecular mass is given as 78. Empirical formula mass, which I can call as EFM, that is the mass of CH, that is 12 plus 1 is equal to 13. So we will divide 78 by 13 and we'll get 6. So N is equal to 6. So what we are going to do is, the molecular formula is equal to CH N, that is equal to CH whole 6 times, that is equal to C6H6. So this is the molecular formula of benzene. So we've taken out the molecular formula and the empirical formula of benzene. Now we'll discuss the law of definite proportions. Law of definite proportions. It is also called the law of fixed proportions, law of constant proportions. Right? Let's consider this molecule, ammonia. Okay. Now, in this molecule, if we consider the atomic mass of each of the elements, then you have nitrogen, which is 14 grams, and hydrogen, it is 1 into 3, that is 3 grams. Or you can say 14 grams of hydrogen combined with 3 grams of 14 grams of nitrogen combined with 3 grams of hydrogen. So the ratio by mass in this case is 14:3, and this is fixed. Irrespective of the source of ammonia, the ratio in which the elements nitrogen and hydrogen combine to form ammonia, that ratio by mass will always be fixed, that is 14:3. Let's take one more example. Let's take water here. Now in this you have 2 grams of hydrogen combining with 16 grams of oxygen, and if we further simplify it, we get 1:8. Right? Now this ratio 1:8, this is the ratio by mass. This is fixed irrespective of the source of water. The water may be of lakes, the water may be of oceans, the water may be from a sea, the water may be of Yamuna, the water may be rainwater, it may be any kind of water, so long as it is pure water. The ratio by mass in which hydrogen combines with oxygen to give water, that is constant, and that is 1:8. Let me take one more example. Carbon dioxide. Here you have 12 grams of carbon combining with 6 multiplied by 2, that 16 multiplied by 2, that is 32 grams of oxygen. To simplify it, we have 4 3s are 12, 4 8s are 32. That is 3:8 is the ratio by mass in which carbon combines with oxygen. Now, irrespective of the source of carbon dioxide, whether you get carbon dioxide by decomposition of calcium carbonate, or whether you get carbon dioxide through respiration, or whether you get carbon dioxide through combustion of coal, of wood, or whatever, irrespective of the source of carbon dioxide, the ratio by mass in which carbon combines with oxygen that will always be 3:8. And this is what you have. This is actually the explanation of law of definite proportions, or law of constant proportions, or law of fixed proportions for that matter. This law was given by Joseph L. Proust, and it says, irrespective of the source of a compound, the ratio by mass in which the atoms in which the elements combine with each other is fixed or constant. Now let me give you an example. Supposing you have, let's say, you have 3 grams of carbon, and you have 8 grams of oxygen, right? Obviously 3 grams of carbon combined with 8 grams of oxygen, and this they give you 11 grams of carbon dioxide, right? Now supposing you have 3 grams of carbon but you have 50 grams of oxygen, then how much carbon dioxide will be produced? Now let's look at the solution to this question. In carbon dioxide, the ratio by mass is 3:8. That is 3 grams of carbon combined with 8 grams of oxygen, right? So 3 grams of carbon will always combine with 8 grams of oxygen. Now suppose you have 8 grams of oxygen, which is already of course there in the formula of oxygen, and it combines with 3 grams of carbon. Let's take it this way. Supposing you have 50 grams of oxygen, then 50 grams of oxygen will be needing 50 into 3 multiplied by 8. That is equal to 150 by 8, and that is equal to 8 ones are 8, 7, 8 eights are 64, 6, 8 sevens are 56. That is approximately 18.7 grams of carbon. Now given to us is only 3 grams of carbon. So if we react 18.7 grams of oxygen, then for this 18.7 grams of oxygen we'll be requiring 3 grams if we react 50 grams of oxygen, then this 50 grams of oxygen will be requiring 18.7 grams of carbon. Okay, so 3 grams of carbon will react with only 8 grams of oxygen, right? And how much grams of oxygen do we have? We have 50 grams of oxygen. So out of 50, 42 grams of oxygen will be left behind, and 3 plus 8, that is 11 grams of carbon dioxide will be produced. Another term actually which we come across here in this law of definite proportions is the concept of limiting reagent. As you can see, in carbon dioxide, or amongst the elements which are given to us, carbon and oxygen, we have 3 grams of carbon and we have 50 grams of oxygen. Okay? 50 grams of oxygen. But though we have oxygen in quite a major amount as such, but it is 3 grams of carbon which is determining how much carbon dioxide will be produced, because it is in limited quantity. So the element or the reagent which is in limited quantity, which is in, you can say, limited or lesser quantity, determines the amount of compound being formed. Amount of compound which is being formed. Okay. So this was law of definite proportions. Multiple proportions. And this was given by John Dalton. Let's consider this. Supposing you have carbon dioxide, or rather, let's say you have carbon monoxide and you have carbon dioxide, that the elements in both the compounds are similar. So you have 12 grams of carbon combining with 16 grams of oxygen here, and here also you have 12 grams of carbon combining with 32 grams of oxygen. The amount of carbon in both the cases is the same. And if you look at this, the amount of oxygen here is 16 and here is 32. If we see a ratio between 16 and 32, it is a simple ratio, that is 1:2. Let's look at one more example. Sulfur dioxide and sulfur trioxide. You have 32 grams of sulfur here combining with 64 grams of oxygen. Same ways, you have 32 grams of sulfur here combining with 48 grams of oxygen. Now the amount of sulfur is same in both of them. If you look at the amount of oxygen here, then you have 64:48. That is 8 8s are 64, 8 6 are 48. You can further reduce it to 2 4s are 8, 2 3s are 6. That is, the ratio is 4:3. One more example, let's say P2O3 and P2O5. Here phosphorus is 31 multiplied by 2, that is 62. And this is 16 multiplied by 3, that is 48. Here you have 62:80. So if we look at, of course, the amount of phosphorus is the same in both of these. If we look at the amount of oxygen, it is 48:80. So this will be 16 3s are 48 and 16 5s are 80. So they bear a simple ratio. That is, the other element which is present in the compound, the ratio in which it combines with the same element. It is a simple ratio. So we can say, as per the law of multiple proportions, the statement of the law of multiple proportions, that is, when one element combines with another, to form more than one compound, the mass ratios of the elements in the compounds what actually mole fraction is. In simple parlance, we can say number of moles of a particular component out of total number of moles. If it's a solution, we will say, supposing we have to find the moles of solute, number of moles of solute upon moles of solute plus moles of solvent. Let's take an example. Supposing we have 180 grams of water containing 58.5 grams of NaCl, and we have to find mole fraction of NaCl. First, let's calculate the molar mass of NaCl and water. So molar mass of NaCl, this is equal to 23 plus 35.5. It is equal to 58.5 U. And molar mass of water is equal to 1 into 2 plus 16, that is 18 U. Now, number of moles of NaCl is equal to given mass upon molar mass. This is equal to 58.5, and 58.5 we had calculated as molar mass. So number of moles of NaCl is 1. The number of moles of water is equal to Given mass of water which is 180 upon molar mass that is equal to 18. So this is 10. Number of moles of water is 10. Now mole fraction of NaCl, this is equal to number of moles of NaCl which is 1 upon total number of moles that is 1 plus 10. So this is equal to 1 upon 11. It is equal to 0.09. So 0.09 is the mole fraction of NaCl. This is how we find the mole fraction.